Welcome to video 28 in the TTB course. This video is from part 6 of the course. In part 6, we wrap up the course. In this video, we present our conclusions. The material in this video is based on chapter 27 and chapter 28 in the ERES2 book. You may like to read these chapters before watching this video. So let's go back to the beginning. Just consider some of the material that we've covered during the course of the last 28 videos. So when we say that an embedded system has a time-triggered architecture, we mean that it executes at least one set of tasks according to a predetermined schedule. The schedule determines the order of the task releases, the time at which each task is released, and whether one task can interrupt or preempt another task. In practice, the usual starting point for TT designs is a bare metal software platform, no RTOS, no Linux, no Windows. We have one active interrupt per CPU linked to a periodic timer tick. All peripherals are polled. So we start the course by looking at a very simple form of TT scheduler, which was based on a timer ISR. We discussed the fact that this gives us a simple time-triggered cooperative scheduler, but it's not a recommended platform for most safety-related systems. We looked at another simple scheduler, this one as described in the PTTS book. Again, this is a good platform for reliable embedded systems, but it has very limited monitoring capabilities, and again, we suggest that you don't use this in safety-related systems. We talked about the importance of thinking in tick lists when you create your TT design, and we've talked a lot about tick lists during this course and seen that these are a key way of modeling time-triggered systems. We've seen that systems may have multiple operating modes, and each operating mode, they're likely to run a different set of tasks, have a different tick list. We've seen that you can hook together multiple microcontrollers in a local or distributed format and do so using a shared clock scheduler. So there's still one interrupt driving the microcontroller on each scheduler in this type of design. On the master node, the schedule is driven by periodic timer ticks. On the slave nodes, the schedule is driven by ticks that are generated when messages are received from the master. In this way, we can synchronize the activity across the network, and as we've discussed in previous videos, we can model this network activity as well. We've seen that we can build time-triggered systems not just using cooperative tasks, but also when we have task preemption. And as we've discussed, we can make the designs immune to priority inversion, unlike designs based on a traditional RTOS. So even when we have task preemption, we can still have highly deterministic timing behavior in our system. We discussed in detail techniques for modeling TT designs with tick lists. And we've seen that there are various things that we can model in this way, such as the system response times, the task jitter levels, and maximum CPU loading. These are all useful things to be able to do, and it's very difficult to provide such detailed information, for example, for the maximum CPU load if you're working with an event-triggered design. So we talked about the importance of CPU load and typical requirements that the CPU load must not exceed a particular value, maybe a customer requirement. And we talked about the fact that when we have a model of the system, it's possible for us to determine whether we can add additional tasks to the system without it having an impact on other tasks. So in a TT design, once we've got a set of tasks, if we add additional tasks after the current tasks in the schedule, if there's space in the schedule, if we add additional tasks, we can do so without having any impact on the tasks that are already included in the task set. This again is extremely powerful. We've ran through techniques for modeling the maximum CPU load and saw this is a very simple process. By now you should be familiar with it. We then went on to consider in some detail the need for runtime monitoring systems. So once we've got our model, we have to accept this model is based on various assumptions. We have an operational CPU in each microcontroller. We can transfer data between microcontrollers without corruption, for example. And we discussed the fact that we need to test these assumptions at runtime, and we need to consider what we will do if the assumptions are not met at runtime. We've talked about various platforms in this course. These platforms are intended to make it easy to create reliable, safety-related embedded systems using a time-triggered architecture with minimal design effort. For example, this shows a duplicator B design involving two microcontrollers with cross-checks between them and an additional external watchdog controller component. This example illustrates the use of this platform to control an industrial robot, but the platform can be applied in automotive applications, industrial control applications, medical applications, etc. We've looked at various examples during this course. One example of the checks that are carried out in such a platform, as we've discussed, is that we will have each microcontroller perform cross-checks to ensure that the tasks being released on the other microcontroller are as expected. This provides very powerful predictive monitoring capabilities for a TT design. We talked in general terms about the differences between the C programming language and MISRA C as a safer subset of the C programming language. In the same way, when we consider time-triggered and event-triggered architectures, time-triggered systems are a subset, a safer subset of a more general class of event-triggered systems. Essentially, in most cases, what we are doing is we're reducing the number of interrupts in the system, making it easier to ensure that we have a controlled number of system states and that we can keep track of whether the system is in an expected state or not during the system execution. We've seen that TT architectures are supported in various international safety standards. For example, they're highly recommended in IEC 61508 designs for systems of safety integrity 2 or above. And there are various other supportive statements in this standard that can help when developing a safety-related design in compliance with IEC 61508 using a time-triggered architecture. As we conclude this course, let's consider some ways in which we can bend the rules a little bit. Suppose we've got an event-triggered design with multiple interrupts. A quasi-TT approach involves reducing the number of interrupts until we get to the point that we can model the design at a level of precision that meets the needs of our application, but isn't necessarily a pure TT design. So we can often improve reliability significantly in this way. And if we end up with one or two additional asynchronous interrupts and short ISRs, then we are likely to still be able to obtain safe behavior with our application. So what we're really doing here is we're saying that unconstrained task preemption, for example, is difficult to model. But if we put constraints on the task preemption, reduce the number of interrupts, then it's much easier to model the system and to become confident that the system will operate safely as required to meet the needs of the application. So how would we monitor a quasi-TT design? We're assuming that most of the tasks will be TT, and we monitor the execution time of tasks, and we monitor the task sequence for TT tasks. These processes are the same as we use in a pure TT design. For the event-triggered tasks, for the tasks that are asynchronous, not synchronized to the timer tick, we'd monitor the ISR execution time. For example, we'd start a timer when the event-triggered ISR is triggered, then follow a similar approach to that which we use for monitoring TT tasks. And we would also expect to monitor the interval between event-triggered ISRs. So if the tasks are called too frequently, or perhaps not frequently enough, we would signal a fault. Overall, this approach can be effective if we have just 1 to 2 additional event-triggered tasks. One of the challenges with such a system is once we start adding 1 or 2 additional tasks, somebody will add a third or a fourth or a fifth, and before very long it becomes much more difficult to be confident that our system will operate as required. There's another option we can consider, a plus TT design, or another way of viewing this is sometimes called use of a TT wrapper in our design. Suppose we've got an advanced driver assistance system. We've got a scheduler and we've got 1,000 tasks, etc. Or we've got an RTOS and a large number of tasks. And this system already exists. At least in the first instance, it probably won't be possible or practical or cost effective to convert this whole system to a TT design. Instead, we will probably have, say, a general purpose processor, perhaps running Linux or a conventional RTOS, or just a bare metal event trigger design, and we would use a TT system to provide increased safety of this system. So here's an example of a similar existing design that you may have come across before. If we have a complicated ADAS system with a TT monitoring system, a similar arrangement is in place in our heads. We have a cortex. This provides higher level brain functions for thought and action. Individuals have imagination. They're difficult to predict exactly how they will behave. We also have a brainstem. This is the lower level brain function. This supports breathing, heartbeat, blood pressure. This is much more deterministic. And it doesn't matter what we do with the cortex. We cannot think, I want to stop my heart from beating now. This just doesn't happen. We're not designed that way. So these designs are carefully partitioned in much the way that we would expect to have a TT wrapper or a plus TT design carefully partitioned in order to ensure safety in various complicated systems where we cannot build the entire system using TT components. There are many areas that we can explore further using this kind of TT wrapper around complex existing systems. That brings us to the end of this course. Thank you very much for listening. I hope that some of the material has been of interest to you.